Hello and welcome to today's video, part one of our log-free programming. In this video, we're going to explore quite some advanced topic and frankly complex topics. We're going to start with sequential consistencies, and we're going to explore memory orderings and the difference between different CPUs. And it's quite the challenge, to be honest, at least for me when I started with this. And the main kind of bottleneck, or the main, the difficulty really resides in shifting perspective. We have to stop thinking about sequential programs because we kind of write programs sequentially. That's the nature of text. It's like, it's a sequence of characters. Like it's the natural way to think about it. But in reality, it's going to be executed in parallel. And that will cause issues, which we will talk about. And the idea or the motivation behind this video is to shift this focus. So we're going to lay foundation for the next videos of where we're actually going to perform or we're going to develop some log-free algorithms. Yeah, again, it's a really complex topic, especially memory orderings for newcomers, that is. And you don't necessarily have to understand everything in this video. So as long as you understand the foundations, as long as you understand or you have an idea of why we have different memory orderings, I think that's a big win. Because in the next video, for example, it's already being prepared. There will be some examples on why, for example, we use different memory orderings here and different memory orderings there. So again, keep an open mind while watching the video. Give it a try. I understand it's a complex topic, but hopefully we can go through it together. So grab your notebooks, take notes, and let's begin. So to start from the beginning, like what is the problem? Why are we talking about memory model? Why it matters? And the reason we're doing this is because that the program that you wrote is, in a sense, not the program that the CPU runs. Or maybe even if the CPU respects the program that you wrote, the output is still different. And so you don't really notice this in sequential program. CPUs are incredibly engineered, and there is a lot going on there. And to squeeze every inch of performance possible, we have to understand what's going on there. We have to kind of account for the different behaviors of every CPU, kind of. And that's why we have to start talking about reordering in a sense. So the first form of reordering is compiler reordering. So if you have, for example, a for loop and you have like x equals 1 and a bunch of instructions, the compiler can see that x equals 1 is within the for loop. But if it's not used in the loop, it's going to reorder it, exactly put it outside, or maybe even after the loop. So that is the first form of reordering. The second form of reordering is that the CPU reorders execution. Now, it doesn't randomly reorder execution. The CPU is incredibly smart. It respects the order of instructions. So if you have a bunch of instructions, the CPU kind of, if you will, a sliding window approach. It looks at n instructions ahead, and it kind of thinks of, okay, which instructions are ready, which instructions are slow. So for example, if an instruction is waiting for data, then it may kind of do it later when the data is ready and proceed with the next instructions, given that there is no dependencies between kind of the read and the following instruction. So it can kind of reorder execution. And another thing which is very relevant to what we're going to see next is that the cache reorders visibility. So the CPUs are, again, they want to be really fast, and so they don't directly interact with the RAM, at least when they can afford not to. And so that's why we have the cache in the middle. And that cache can, in a sense, reorder visibility, and we're going to see how. So before we start, we're going to talk about the fundamental memory model Sequential Consistency by Leslie Lamport, the GOAT. So sequential consistency is kind of the standard or the go-to model It's a specification, sort of, and it's fundamental. I can't really say too much about it, and it's a very simple concept. The idea is that the program order is preserved in a multi-threaded environment. It's actually incredibly simple. There are two criteria. So if we have a multi-threaded program, we have thread A and thread B, and we suppose that we have a single CPU in our machine, CPU 0. So criteria number 1 is that the CPU can only execute one instruction at a time. Criteria number 2 is that the CPU respects the thread's order when executing. So if we suppose that thread A has 3 instructions, A0, A1, A2, thread B has 2 instructions, B0, B1. So at instant t equals 0, so at the very first start, we have 2 threads, the CPU just kicked off. It's going to pick thread A or B. Sequential consistency does not dictate how the CPU should pick threads. What it dictates is that it should respect the program order. So if it picks thread A, it needs to start with the first instruction in thread A. If it picks B, it needs to start with B0 as well. And so let's say it executes A0. So this is done. What next? It can either execute A1 or execute B0. So it cannot jump into an unexecuted instruction or into an instruction that is not following the last executed instruction. That's the idea. The sequential order of threads is preserved. So these are our 2 rules. And we're going to kind of build a hypothesis under this rule. So let's learn what kind of sequential consistency guarantees through an example. So we're going to have 2 shared variables between 2 threads, x equals 0 and y equals 0. Then we have 2 threads, thread A and thread 1 and thread 2. So in the first thread, we're going to set x to 1 and r1 to y. And thread 2 is going to set y to 1 and r2 to x. So if we were to execute this, of course, we know that the CPU can pick different combinations of threads and their instructions. But is there a world, is there a universe where under these 2 rules that we have defined, that we end up with r1 equals 0 and r2 equals 0 at the same time, by the time the CPU executes all the instructions? So let's figure it out. For simplicity, I'm going to name this thread A and thread B. First instruction A0 and A1, B0 and B1. Now again, we have one single CPU that can run only one instruction at a time, right? So what are the possible combinations that the CPU can execute that are correct under sequential consistency? So we can start with A0 followed by A1, for example, into B0, B1, or we can start with A0 followed by B1 followed by, that is forbidden, A0 followed by B0 followed by B1 followed by A1, right? That is also correct. The order of each thread is preserved, kind of interleaving these 2 threads. And another case, we could have, let's see, have we exhausted A0? So from A0, we can either jump here or here. Yeah, I think we could also do A0 into B0 into A1 into B1. I believe that's it. Because from here, we can jump here. And from here, we can either jump here or jump here. Yeah, I think that should be it. If I missed something, let me know. And the same for essentially starting with B0. We can also do B1, then A0, then A1, or B0, A0, A1, B1, or B0 and then B1, A0 and A1. All right, so your task is to essentially, we have 6 scenarios here, hopefully I didn't miss anything, and compute the output and see if this condition is ever true or is true in one of these combinations. So take your time if you want, and yeah, do the math. Well, it's not really math, but it's hand execution. So pause the video, take a couple of minutes, and when you're ready, resume. But real CPUs do not deliver sequential consistency. You're like, what the hell? I didn't even execute. Well, yeah, you will get, that condition is never reachable. So in real CPUs, however, it is reachable, which means they break the sequential consistency rule, and we're going to see how exactly that happens. So on a real CPU, we can actually end up with, what was our condition again? Yes, R1 equals 0 and R2 equals 0. So it is completely possible. And to understand how this could happen, this is where we're going to have a deeper look into the hardware, and especially the store buffer. The store buffer is a queue, just going to note it as a queue, and it's a first in, first out. But this first in, first out is, take this with a grain of salt, because this depends on the hardware, or rather depends on the CPU. For example, it can be first in, first out on x86 CPUs. For example, AMD, it may not be the case. So, but it's a queue. And the idea is that the store buffer belongs to a core, right? These two cores could be part of the same CPU, right? You have one CPU with 2 cores, but the store buffer belongs to core, like store buffer 1, for example, belongs to core 1. Store buffer 2 belongs to core number 2. There is a general idea. So maybe this would be too much information, but the idea is that a core could see what's in its own store buffer, but it cannot see what's in other cores' store buffer, right? So following the exact same scenario from earlier, we have a shared cache between both cores, where we have x equals 0 and y equals 0 initially. So what the store buffer is used for is that when we have a store operation, like storing 1 into x, the CPU is not really going to grab the value and throw it into the cache. Instead, it's going to emit an entry into the buffer. So it will store into the buffer x equals 1. And then it can also keep storing different things here. And then at some point, at a given time, the store buffer is going to be drained into the cache. So this happens asynchronously. So it means the CPU could still be executing, for example, R1 equal Y, and this store is still not set into the cache just yet. So there are different things that really dictate when the drain should happen. But as far as we're concerned, and what the safe assumptions that we could make about the draining of the store buffer is that it's asynchronous, and we don't really know when it happens, and so we cannot really dictate when it can happen. So it's not really within our control, so to speak. So that is part of the CPU, to control when the draining should happen. So what we know, or what we should know, is that the core will emit store instructions into the buffer and then move to the next, because it really wants to go fast. It doesn't want to wait for things. It doesn't need to wait for. And yeah, same thing also for core number 2. All right. So let's look at a case where we already queued x equal 1 into the store buffer. Meanwhile, we have queued y equals 1 into the store buffer of core number 2. And the items now are still in the store buffer. We still haven't updated the cache. Next, we're going to queue R1 equals Y. And to queue R1 equals Y, this is actually load Y, right? We have to see the value of Y and then store into R1 the value that we just loaded. So it's 2 instructions here. And the problem is the load. So when we're going to load Y, we're going to find it in the cache, and guess what? Y equals 0. So it's essentially, we're going to be emitting into the store buffer R1 equals 0. This exact same logic happens on the other side. We still have Y equals 1 queued here. And then we're going to essentially, honestly, at this point, even if we write Y equals 1, even if this has drained, we have already queued R1 equals 0 in the store buffer. So it doesn't matter what's in here at this point. But what we're going to do is that we're going to set R2 to X. And again, we're going to load the value of X. And this one is still in the queue. And it hasn't been drained. So we're going to read 0 because that's what's in the cache. And so we're going to emit R2 equals 0. And eventually we're going to end up with R1 equals 0 and R2 equals 0 in the cache. And so this is an example where essentially sequential consistency has been violated, and thanks to the store buffer. So the store buffer is there for a reason. It's to make the CPU go fast. Like it's not there to hold us down. So when you write a sequential program, you don't use multi-threads. Your program is fast thanks to this. So this only happens, or is only a concern if you're writing multi-threaded programs. And the behavior that we just observed is store load ordering. And it's one kind of an ordering. There are multiple kinds of ordering. There is, for example, store ordering. There are different kinds of ordering. We're going to kind of see not the difference between them, but what kind of orderings are allowed and what are not allowed. And so memory model essentially dictates what ordering is allowed and what ordering is not allowed. So for example, x86 total store order is almost sequentially consistent. And x86 is the strongest relaxed memory model in mainstream use. These are two opposite poles, if you will. We have strong, think of it as like a slider, and we have relaxed. And so x86 is, I was about to write 64 for some reason. So x86 is kind of the strongest relaxed because it's still relaxed. It's not 100% sequentially consistent. And that's why we kind of had to learn what sequential consistent is, because it is basically strong is equivalent to sequential consistency. So x86 is the strongest relaxed memory model. And the reason for that is the CPU basically allows only for one sort of reordering, which is the store load reordering that we just observed. And as you may have guessed, there are different CPUs that fall in different categories in the slider. And that is kind of the default behavior of these CPUs, which means what you should expect. And you should write what memory ordering allows us to do is to take that into account and specify saying like, oh, I don't want this kind of ordering, but I can tolerate this kind of ordering, for example. For instance, ARM and PowerPC, they have weak ordering or relaxed ordering. And the reason for that is because ARM, for example, is mostly used for embedded devices, right? You find them, you find them mostly in your phone or, for example, on Macs, right? I think they're using them, even though it's embedded, it's actually recently discovered that it's the M1 chips are actually quite efficient but it's kind of a decent balance between performance and power consumption. So it's not kind of necessarily embedded, but it still has a weak memory ordering, and you have to take that into account. So when you're writing your code on an Intel processor, you have like an amazingly fast, like lock-free, database, and then, you compile it on Mac, and then, weird things happening. So that's most likely memory ordering. So ARM and Power essentially allows almost anything. So stores can reorder with stores, load can reorder with load, and loads can move before earlier stores, all sort of combinations exactly. And you may be wondering why, right? Why is this allowed? Actually, this is kind of it's a design decision that the manufacturers make. For example, if your program doesn't need sequential consistencies, then it is faster for the CPU to make all kind of reordering that it wants. It makes it faster or it makes it more efficient. However, if you set constraints and you say, I want this memory model, it might be a little bit less efficient for the CPU. So your program might be slower, but it's consistent. And that is the idea. That is why different CPUs have different behaviors. Because realistically, they kind of target different things. And also they give you different flexibility as well. So the idea is that the memory model is, at the end of the day, a contract. So for example, ARM processors gives you exactly the memory ordering that you request. If you request a relaxed memory model, you're going to get a relaxed memory model. x86, on the other hand, if you request a relaxed memory model, it's still going to give you a stricter, stronger memory model, because that is kind of the minimum that it supports. And that minimum defines the consistency of your program as well. So C11, we talked in the last video about atomics, I believe. And also it provides orderings that we can choose from. And there are a total of 6 orderings that we can choose from. So for example, if we have atomic store explicit, and we can specify that we want memory order release. Or for example, we have a load explicit, we can request memory order acquire. And basically you pick one, right? You choose the memory order that you want. And based on the target hardware that you're in, so if you're compiling for x86, it may not do anything. So it may essentially be a direct load, because x86 doesn't have relaxed memory ordering. But if you compile it on ARM, for example, you might see some barriers. You might see some CPU instructions inserting barriers so that the memory ordering that you specified is consistent, or is preserved rather, during runtime. There are 6 orderings in total, but consume is actually, it's every compiler kind of just moves it to acquire. It's supposed to be a more relaxed version of a compiler, but in practice it's not really used. So I would recommend that you don't use this. So we're going to kind of see in details what each of these orderings do. And the idea is that we are going from relaxed to more stronger orderings. And I really believe that it's better to see these through examples rather than definitions. So the choice of ordering, in a sense, is the single most important decisions in lock-free programming. And that's why it's better that we review them in practice rather than just walk over the definition. And this is what the next 4 parts of the series are really about. All right, let's look at some example using our new orderings. And the first example that we're going to review is message passing. And so the idea of message passing is that we have 2 threads, thread 1 and thread 2. We're going to have, they share, of course, some data. And we want to have one thread writing in that data and So this would be a write operation. Another thread is going to read. So this is going to be a read operation. However, we want to make sure that the writer gets to write the data first before the reader gets to read it. And so to do that, we're going to need a synchronization atomic. And so we're going to use an atomic, right? And essentially what's going to end up happening is that this is going to be a flag. I'm just going to draw it a square. This is going to be a flag. And so once T1, thread 1, writes the data safely, so it writes whatever value it wants over here, then it sets the flag to 1. And then T2, it is not allowed to read data unless or until the flag is set to 1. So once it observes that the flag is set, it can read the data. And so this is the idea of message passing. So we have a message that we want to emit, but of course you cannot concurrently read and write from the same variable. We know that leads to issues. And so we're going to create a synchronization point essentially through this atomic. All right. So through a concrete example, we have our shared data. So in data equals 0, and then we have our atomic ready set to 0. So we have two threads, a producer and a consumer. So the producer wants to publish the data and the consumer wants to receive the data. So the producer is going to set the data to 42. That is the desired value. And then it's going to set the flag to 1 via memory order release. So this is the first memory order that we're going to review. Thread 2, on the other hand, is going to continuously load the ready flag via memory order acquire. And if that flag is not set, it's going to try again until it succeeds. And then it asserts the data is equal to 42. So it checks if we actually got the right value. So normally via normal approach, you would just set a mutex, right? But we don't want to do that. We want to use atomics for synchronizations. We don't want the thread to sleep. And one good argument here could be, for example, that we're sharing a simple message. We don't really need to put the thread to sleep, for example, or something. So now we're going to observe what this memory order gives us, in a sense. So to kind of summarize what these threads do, I'm going to kind of draw the main instructions, if you will. So we have a store data 42 over here, and then we have a store ready 1. All right. On the other thread, we have a load ready, right? And then we also have a load data. So yes, we do have, some things in between. We have a while loop, we have a comparison, but that doesn't matter. We only care about kind of the flow, the data flow rather, not the instruction flow, right? We care about store and load reordering. All right, what's important is that this load is memory order acquire, and the store is memory order release. So I'm going to talk about the technical implications first, and then what this gives us on a high level. So memory order acquire, it's like a breaking point where after this instruction, the CPU is not allowed to reorder, or rather the CPU is not allowed to reorder previous stores to be after this memory order release storing. So the idea is that if the CPU decides to move setting data to 42 to after the store, it actually cannot. This is what the memory order release gives us. It cannot do this. So it essentially cannot reorder any essentially stores after this instructions. And acquire, on the other hand, it's the same concept, right? So the CPU is not allowed to reorder any load that happens after the memory order acquire load. So it cannot move anything before to happen before this instruction. So in a sense, the acquire forbids reordering to be after. So everything that we have before must happen before this instruction. And release, on the other hand, everything that happens after this instruction must indeed happen after it. So nothing from down here comes on top. And store, on the other hand, nothing from before our memory order release store to happen after it. So in a sense, one guarantees some level of ordering for writes, and the other guarantees some level of ordering for reads. And this is what the property that we want to. This is why we're using memory order release and acquire. However, one small difference is that, let's say here we have store 1, store 2, right? And then we have store data 42, and then store ready 1. The CPU is still free to reorder these things around, as long as they don't go past our store ready 1, right? So it can reorder anything before, but for us, this is the barrier. This is what matters. And essentially what this gives us, it gives us a synchronization point. So the idea is that by the time ready is set to 1, we know for a fact that data is set for 42, which means that by the time ready is observed to be 1 in thread number 2, data is guaranteed to be equal to 42 as well. So, and it also, of course, here it guarantees right order of reading things as well. That's why we have to use memory order acquire, because if you read data before ready, then it defeats the purpose. So the TLDR is that memory order release and acquire together, they form a synchronization point over a single atomic. So we're using ready here as a flag, or as our synchronization variable, kind of. And the message that we want to pass in this case is data. And this is how we safely pass messages. So to summarize, the release and acquire memory model makes it safe for the producer-consumer model. And so this is kind of the pattern that you would use when you're writing such threaded programs. So if you have a producer-consumer model, then release acquire may be the memory model that you would want to use. And under this memory model, assert cannot fire because when thread 2 sees ready equals 1, the data is ready equals to 42. It is guaranteed to be visible as well. So as soon as that flag flips, the data is guaranteed to be visible. And yeah, if we use relaxed, then assert can fire, right? Because the CPU can reorder the data equals 42, right? Which, to happen after setting the flag ready to 1. And so, yeah, that can mess things up. All right, let's move to another example, a store buffering example. So if you look at the code, you may notice that this is the exact same code example that we have used to define sequential consistency. The logic is as follows. We have two shared variables. And then we have an atomic store. So we're storing 1 into X. And then we're storing, or rather we're loading Y into R1. This all happens in thread number 1. In thread number 2, it's the reverse logic. We are storing 1 into Y, and then we're loading X. So we're fetching X into R2. So the question is, can we end up with R1 equals 0 and R2 equals 0? So I'm going to skip and say, yes, we can, unfortunately. And here is why. So first let me clean the board. All right. So we're going to start with thread 1. What we have, the first line in thread 1, we have an atomic store explicit with memory order release. And release essentially protects what is before this instruction. So no instruction above this line can, or no store above this line, actually it protects both stores and load. So no store or load above this line can jump after it. So that is a rule. And memory order acquire protects everything that is below or past this, if you will. So nothing from below can jump before or above this line. So this is what memory order release and acquire gives us when used together like this. However, there is no rule or there is no scenario that specifies that we cannot swap these two. So which means we can actually perform a store load ordering or reordering. So this swap is completely valid. The reason why this pattern is fragile is because there are different scenarios that can happen when running two threads. So we don't really know what the CPU is going to reorder. And with this model, we're not actually specifying what should happen, but we're specifying what should not happen. And that is the mental model that you have to take into account when writing lock-free algorithms. So there are a lot of combinations, a lot of reordering that could happen. And we're essentially telling the CPU, like, you can do whatever you want, just don't do this and that, right? This is what we're telling the CPU. So we're kind of locking specific scenarios. And so again, back to this example that we have, and I'm just going to reiterate it one more time because it's extremely important. Memory order release. Again, it states that anything above this line can be reordered as long as it is above this line. So the CPU can reorder instructions around, but nothing from above jumps below, right? It's forbidden. So I'm going to remove that. The same thing with memory order acquire. Everything past this can be reordered. So the CPU can reorder instructions past this, store load instructions, but nothing from down here can jump above the memory order acquire. So this is not allowed. However, because one protects the upper half, so to speak, and the other protects the lower half, there is nothing that really protects the swap of these two together. So the CPU can actually perform the atomic load explicit and then the atomic store explicit under these memory order acquire and memory order release. And so if this happens for both thread 1 and thread 2, then we end up with R0 equals 0 and R2 equals 0. So in summary, we have thread 1 and thread 2. They both have a store and they both have a load. Literally the same code, except they're kind of using different variables. And because store protects the upper half and load protects the bottom half, there's nothing that dictates that these two should not be swapped. Hence, if the CPU swaps them, if it loads if it loads y into R1 with y being 0 initially, we're going to end up with R1 equals 0. And then in thread number 2, if it also swaps the order and loads x into R2, we're we're also going to end up with R2 equals 0, and then it performs the store. And so this is definitely a reachable scenario. Again, this is the same example where we discovered sequential consistency, and only sequential consistency forbids, memory model forbids this outcome. And so basically what we have to do is memory order here is going to be sequential consistency. So with that being said, let's see what the compiler emits for different memory orderings. So we will compare primarily x86 instructions and ARM instructions. So remember that x86 is a family of CPUs. So that is things like Intel, AMD. Personally, these are the only two I know, and you have ARM processors, M1 chips, etc. So notice that if we have for all of these, the compiler actually emits move instructions. And that's because x86 has like its lowest, it is the strongest, most relaxed CPU basically. That's its default memory model. So even if we specify a memory model relaxed, it's just going to translate into move, and that is perfectly fine because then you can compile your code, for example, targeting ARM architecture, and it is going to compile into the right essentially instructions. And so roughly like relaxed, it doesn't have any overhead. So if you use, for example, acquire or release, there is a slightly more overhead. And then if you go into more sequential guarantees, essentially you're going to end up with even more penalties because it's going to have to add fences, for example. Of course, this cycle over here is more about the ARM instruction. So for example, on Intel, for the load of the sequential consistency memory model, it's just a move, but the store is fenced. So what we need to remember at the end of the day is that memory model is just a contract. Some architectures over-deliver, so they guarantee a bare minimum. Some architectures do not. They just obey the memory model that you specify. For example, most memory models are free on x86. We have also seen how basically a sequential consistency load is essentially free. So it literally compiles to move, while on ARM it doesn't, and it costs more. So we have to take all of these architectures into account, unless, of course, if you are compiling into like an x86, then it makes sense, for example, to not care about other architectures. So the question is, why not? So there is the fundamental kind of TLDR, if you will, just the high level keywords. And hopefully you have learned more than that. Moving forward, in the next section, we're going to not talk about locks, or rather not only about locks, but building blocks. So essentially we're going to see how we can use everything we have learned today to start building some algorithms. All right, this has definitely been a pain to record. So yeah, hopefully you have learned something. You probably see that I have skipped slides because there is just lots of amount of information, and I don't really want to record hours long videos. Not only because it's boring for you, but also it's bad for my throat. So thank you for watching. See you in the next one. Bye bye.